Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Colin Maclaurin's Treatise on Fluxions, published in 1742, stands as a monumental defense of Newtonian calculus against the criticisms levelled by George Berkeley. This essay undertakes a critical examination of the treatise, meticulously analysing its claims and arguments section by section. The goal is not simply to summarise Maclaurin's work, but to dissect its reasoning, evaluate its evidence, and assess the validity of its conclusions within the context of 18th century mathematical discourse. This exploration will determine the work's enduring impact on the development of calculus and its role in solidifying a particular understanding of infinitesimals and their application. Section 1, Introduction to Fluxions and Geometric Exposition. Maclaurin initiates his treatise with a detailed explanation of fluxions as rates of change generated by continuous motion. His approach is deeply rooted in geometric reasoning. Mirroring Newton's original conception of calculus, he presents fluxions not as abstract algebraic symbols, but as inherent properties of geometrical magnitudes such as lines, areas, and volumes. Maclaurin asserts that these magnitudes can be considered as generated by continuous motion, positing that the velocity of this motion represents the fluxion. A critical assessment of this initial premise reveals Maclaurin's intent to ground calculus in intuitive geometric principles, aiming to circumvent the metaphysical objections to infinitesimals raised by Berkeley. He argues that the conception of motion is more accessible and less problematic than the idea of infinitely small quantities. The validity of this claim rests on the assumption that the notion of continuous motion is, in itself, less open to philosophical scrutiny. It presumes a common understanding of how geometrical objects are generated in a temporal space, and that those generated objects can be used to describe change as velocity. However, a further exploration is required to evaluate the effectiveness of this grounding in the face of ongoing critiques concerning both the nature of motion and the nature of continuous change. Maclaurin uses geometric illustrations to demonstrate the relationships between quantities and their fluxions. For instance, he derives the fluxion of a rectangle formed by two varying sides by considering its increment as the sum of two smaller rectangles, each representing the product of one side's fluxion and the other side's magnitude. This illustration is presented as a clear and intuitive demonstration of the product rule in differentiation. However, this rests on the assumption that such a geometric dissection accurately reflects the underlying principles of calculus and adequately justifies the algebraic framework that stems. Section 2, Demonstrating the Fundamental Theorem of Calculus. A central claim of Maclaurin's treatise lies in its rigorous demonstration of the fundamental theorem of calculus. He dedicates considerable effort to establishing the inverse relationship between fluxions and fluents, terms equivalent to derivatives and integrals. Maclaurin presents several elaborate geometric proofs to illustrate this relationship. For example, he considers the area under a curve as a fluent, generated by the motion of an ordinate along the abscissa. He then demonstrates that the fluxion of this area is equal to the ordinate itself, establishing the basic idea that the rate of change of the area under a curve is equal to the height of the curve at that point. A critical point in evaluating this demonstration involves understanding how Maclaurin manages the concept of infinitely small increments within a geometrical framework. He avoids explicitly invoking infinitesimals as actual, defined quantities, instead relying on the notion of limits. This is a key distinction from many earlier approaches to calculus, and illustrates his response to Berkeley's criticism. Maclaurin's argument strength lies in his use of classical geometric proofs, which were readily accepted by the mathematical community of his time. However, the modern reader requires careful analysis to see how these geometric proofs translate into modern analytic formulations of the fundamental theorem. Maclaurin must bridge the gap between geometric intuition and the more abstract algebraic language of calculus. Furthermore, the success of Maclaurin's approach hinges on the precision and clarity with which he defines the limiting process, ensuring that it avoids the logical pitfalls that Berkeley highlighted. He aims to show that calculus can be founded on solid geometric ground without relying on any suspect infinitesimal. Section 3. Applications to problems of maxima and minima. Maclaurin applies his theory of fluxions to solve problems involving finding maxima and minima of curves. He explains how to find points where the fluxion of a quantity is equal to 0, indicating the point of maximum or minimum value. Maclaurin illustrates this method through a variety of geometrical examples, such as finding the dimensions of a rectangle with a given perimeter that maximizes its area. He systematically demonstrates how to express the area as a function of one variable, take the fluxion with respect to that variable, set the fluxion equal to 0, and solve for the value of the variable that yields the maximum area. The strength of Maclaurin's approach in this section lies in its concrete application of calculus to practical geometrical problems. He provides vivid examples of how fluxions can be used to optimize various quantities, demonstrating the usefulness and power of the method. But an evaluation of his approach requires scrutiny of his assumptions and the rigor of his reasoning. For instance, he often assumes that a stationary point automatically corresponds to either a maximum or a minimum, without always explicitly proving that the second fluxion satisfies the necessary conditions. Furthermore, while Maclaurin's geometrical examples are compelling, it is worth considering how readily those examples can be generalized to a wider class of optimization problems, particularly those that lack a clear geometrical interpretation. Are there limitations to his largely geometrical approach in tackling more complex, non-geometric challenges? Section 4. Tangents. Curvature are geometrical properties of curves. A significant portion of the treatise on fluxions is dedicated to exploring the geometrical properties of curves using the methods of calculus. Maclaurin shows how to find tangents to curves, determine their curvature, and calculate their evolutes. He derives formulas for the radius of curvature, the centre of curvature, and the equation of the evolute. These derivations are heavily reliant on geometric arguments and the concept of fluxions as instantaneous velocities. For example, he finds the tangent to a curve at a given point by considering the limit of the secant line as the 2 points defining the secant approach each other. He uses fluxions to express the slopes of these lines and then finds the limit to determine the slope of the tangent. Maclaurin's analysis of curvature provides a deep understanding of the geometry of curves. He demonstrates how the second fluxion can be used to measure the rate at which a curve bends. Again, it is crucial to subject these claims to critical evaluation. While Maclaurin's geometric derivations are elegant and insightful, they rely on a particular way of visualizing curves and their properties. It is important to consider whether this geometric approach is sufficiently general to encompass all types of curves, particularly those that may not have a straightforward geometric representation. The success of Maclaurin's approach hinges on a blend of geometrical intuition and analytical rigor. In cases where geometrical intuition falters, does the framework still afford sufficient means of solving? Section 5. Applications to mechanics motion of bodies. Maclaurin applies fluxions to analyze the motion of bodies under various forces. He investigates problems such as projectile motion, the motion of pendulums, and the motion of bodies on curved surfaces. His approach involves expressing the forces acting on a body as functions of its position and velocity, then using the principles of calculus to derive equations of motion. For example, in analyzing projectile motion, Maclaurin considers the force of gravity acting on the projectile and uses fluxions to determine the projectile's velocity and position as functions of time. He derives equations for the range, maximum height, and time of flight of the projectile. When evaluating this section, it's helpful to scrutinize the simplifying assumptions Maclaurin often makes. For instance, in his analysis of projectile motion, he typically neglects air resistance, which can have a significant impact on the actual trajectory of a projectile. Then, there is the crucial question of how Maclaurin's approach compares to alternative methods of analysing mechanics problems. Did other competing methods afford better solutions, or prove more comprehensive in dealing with mechanics problems? Furthermore, it is crucial to assess the extent to which his findings are empirically validated by experimental observations. This validation helps establish the real-world relevance and practical value of his calculus-based methods. Section 6: Infinite Series and Their Applications. Maclaurin dedicates a considerable portion of his treatise to the theory of infinite series and their application to various problems in calculus. He discusses methods for expanding functions into infinite series, such as Taylor series, which is often referred to as Maclaurin series when evaluated at zero. He demonstrates how to use infinite series to approximate the values of functions, solve differential equations, and evaluate integrals. For example, he expands the sine function into an infinite series and uses this series to approximate the value of the sine function for small angles. Maclaurin's contribution to the theory of infinite series is significant. He provides a systematic approach to representing functions using infinite series and demonstrates the power of this approach in solving a wide range of problems. However, there are challenges in evaluating his approach when it comes to convergence and divergence of infinite series. Does Maclaurin address the conditions under which an infinite series converges? If the series diverges, does he still account for the implications of its divergence? The practical implications of Maclaurin's work on infinite series are profound. He demonstrates how to use infinite series to approximate solutions to problems that cannot be solved exactly, which opened new avenues for tackling complex mathematical problems. Section 7: Differential Equations Solving Problems of Geometry and Physics. Maclaurin delves into the theory of differential equations, presenting methods for solving various types of differential equations that arise in geometry and physics. He demonstrates how to find solutions to first-order and second-order differential equations, and he applies these techniques to solve problems such as finding the equation of a curve given its differential properties or determining the motion of a body subject to a given force. Maclaurin shows how to solve differential equations using a variety of techniques, including separation of variables, integrating factors, and power series methods. Maclaurin's work on differential equations is a critical component of his treatise. He demonstrates the power of calculus in solving problems that involve relationships between functions and their derivatives. However, it is important to consider the limitations of his approach. Does Maclaurin address the question of uniqueness of solutions to differential equations? Are there certain types of differential equations that are beyond the scope of his methods? How does Maclaurin's approach to solving differential equations compare to alternative methods available at the time? It is particularly important to assess its effectiveness in comparison to Euler's methods, which were developing at around the same time. Maclaurin's work on differential equations represents a significant step forward in the development of calculus, providing mathematicians and physicists with powerful tools for solving a wide range of problems. Section 8: Dealing with Imaginary Quantities. Maclaurin addresses the issue of imaginary quantities within the framework of Fluxions. He proposes methods for handling expressions involving the square root of -1 and explores how these quantities can arise and be interpreted within the context of calculus. While some mathematicians were wary of imaginary numbers, Maclaurin attempts to incorporate them into his system. Consider the implications of Maclaurin's approach to imaginary quantities. Were there any inconsistencies introduced into his system as a result of incorporating them? Did his treatment of imaginary quantities lead to new insights or discoveries, or did it primarily serve to defend the existing framework of Fluxions? Compared to other mathematicians of his time, did Maclaurin's treatment of imaginary quantities contribute to their wider acceptance and understanding, or did it reinforce skepticism about their validity? Section 9: The nature of infinitesimals. Maclaurin's defense. Maclaurin's treatise is fundamentally a defense of calculus against the attacks on infinitesimals made by Bishop Berkeley. Throughout the work, he meticulously constructs arguments designed to avoid the logical pitfalls that Berkeley exposed. Maclaurin argues that calculus can be grounded in the concept of motion and limits, rather than relying on the problematic notion of infinitely small quantities. He attempts to demonstrate that the results of calculus can be rigorously justified without resorting to questionable assumptions about the nature of infinitesimals. Maclaurin's approach has its limitations. While he successfully avoids the most blatant logical inconsistencies associated with infinitesimals, his reliance on geometric intuition and the concept of limits may not fully satisfy all critics. The question of whether Maclaurin's defense of calculus is ultimately successful is a matter of ongoing debate. While he provides a comprehensive and rigorous treatment of the subject, some mathematicians and philosophers continue to question the foundations of calculus and the validity of its methods. Some would argue that a truly rigorous foundation for calculus was not established until the development of modern analysis in the 19th century, which provided a more formal and abstract framework for dealing with limits and continuity. Section 10. Contemporary reception and later influence. The treatise on Fluxions was widely acclaimed during its time and helped to solidify Newton's calculus as a dominant mathematical framework. The work was praised for its rigor, clarity, and comprehensive treatment of the subject. Maclaurin's treatise became a standard textbook for mathematicians and scientists for decades, influencing the development of calculus and its applications in numerous fields. It is crucial to assess to what extent Maclaurin's treatise on Fluxions succeeded in its primary goal of defending calculus against Berkeley's criticisms. While Maclaurin's work was well received and widely used, it did not entirely silence the critics of calculus. Some mathematicians and philosophers continued to question the foundations of calculus and the validity of its methods. It is also interesting to examine the reception of Maclaurin's work outside of the scientific community. Did his treatise have any impact on philosophy, theology, or other fields? The treatise on Fluxions had a lasting impact on the development of calculus and its applications. Maclaurin's work helps to establish a solid foundation for calculus and its use in solving a wide range of problems in mathematics, physics, and engineering. Conclusion. Colin Maclaurin's treatise on Fluxions stands as a significant achievement in the history of mathematics, particularly in its defense of Newtonian calculus through rigorous geometric demonstrations, insightful applications, and a careful avoidance of problematic infinitesimals. Maclaurin presented a compelling case for the validity and utility of Fluxions. While not without its limitations, the treatise served as a critical text for generations of mathematicians and scientists, solidifying the foundations of calculus and paving the way for its continued development. Its enduring significance lies not only in its mathematical content but also in its demonstration of how to ground abstract concepts in tangible, intuitive principles, a lesson that remains relevant in mathematical discourse today. The essay's section-by-section evaluation suggests that while Maclaurin's treatise faced constraints in completeness, it delivered valuable insights that contributed to the historical development of infinitesimal calculus.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.